Okay, good morning. Welcome to Krishna's class. We continue with our discussion on continuity defined through sequential convergence. And in fact, we see that in many situations, this definition is extremely easy to verify in a metric space. Now we shall look at some examples in this regard. But you recall that if you have continuous functions, then see the relations like if f g belong to 0 1, say that is all continuous functions are interval 0 1, and d is a metric on that d f g is defined by supremum of gt, and for that matter some other metric also. So you can talk about convergence of sequences, and one can prove that fg belongs to c 0 1 implies where f and g are real valued functions or even complex functions. What we have is that f plus g is zero 1 fg the same under the same conditions and third condition is alpha f or af belongs to we are working in the complex space, then of course you can see also. So these are some of the results that you have, and we shall see the consequences of this. So more generally what we have is that we are talking about continuous functions from a metric space to R. That is the case. There also we have with a usual metric f plus g, fg product fg and af belong to first the metric that you use on this is that that's a generalization of that. Okay. So now let us see. I mean, they are all very easy to prove because you know that, as I have suggested last time, because Fn converges to what you have is this, the following, that is if xn converges to x, in the uh, metric that you have induced here, fx, because f is continuous. And one can easily prove that from this you see that f plus g x by definition, and if f plus g xn equal to f xn plus gxn, and if f and g are continuous, this converges to fx plus gx, which is equal to f plus g. Similar arguments work for fg as well as a. Okay. So that's easy to. So it's quite easy to work with the sequential convergence definition of continuity. Now, one of the examples, any polynomial function in n variables x1, x2, etc., xn is continuous the variables is continuous so you look at P as a map from Rn to defined by, so the general form of P is the following: Px, x is equal to this is equal to summation n, these are all constants indexed by this multiplied by x to the power x1 to the power I1 xn to the power a. These are all, so this is a finite sum. Okay, so you have a, this is a finite sum. Now this is a polynomial in n variables x1, x2, etc. Now, what are the basic functions that go into it? See, if you look at this one, so you can write f I1, I2, etc. In of x, you write as x1 to the power I1, xn to the power product of these powers. So this is essentially a linear combination of these functions. Okay. Now, How do you conclude that this is continuous? See, if you can conclude that each one of this is continuous, then scalar multiples of each one of them is continuous, and then their sum of continuous functions is again continuous. So we make use of these three things together. Okay, but how do you conclude that this is continuous? This is continuous can be used, proved using a repeated application of this. If f and g are continuous, then f g is continuous. So you see that x to the power I1, x to the power I2, etc., x to the power In, they are all continuous real valued functions. Okay, and then you take the product of them. The product is certainly continuous. So use this method to prove this result. So essentially, it is a repeated application of the various parts of this. Once you recognize that this is a finite sum. Once you recognize that P is of this form, then a repeated application of this result would lead you to the conclusion. Therefore, all polynomials in n variables x1, x2, etc., xn are continuous functions. That's the conclusion. Very useful result. Now, some of the results of this kind is this. Suppose you look at take m in R. Take this as, or write this way. So these are all n by n matrices with real entries. Now, what one can prove is this. Suppose you define look at the expansion of the determinant and follow easily. So another example. 1, 3, so let x d define by f of x y equal to Or let me write it this way. This means in a metric space you are, suppose this is the metric space X you are talking about. You fix an element Y and then you are writing down the distance from Y to X as the function. Now what we say is that Fy for each that's also very straightforward, true. Just work on the definition and you will get this. So what you have to prove here is, see, you have to prove that d x and y goes to converges to x. So this is what you have. Okay. That's easy to prove. Or suppose you take f from c/0, it's a punctured S1, that is a unit circle in the complex plane, which is defined as so f said you define by so if Z then converges to Z, then of course you can show that. You remember that the D Z1 Z2 in this case is defined as a simple verification. F from C defined by conjugate, that is F Z equal to Z conjugate, and F is now this is of course uses the fact that Now what we can prove is a small result which talks about the composition of functions. So let x dx, y dy matrix spaces. So we define functions f from x to y and from g from y to z. Now this is what it is. Take an x here, then x gets mapped to, then fx gets mapped to g of, therefore this is the function that you have. This is called g composition. Now it's quite easy to prove this. Now this is a theorem. So let me So what you have is this. The proof is very simple. It says that means no, f is continuous. that is the sequence. The sequence or what you have is dy of 0 because f of is continuous. Since g is continuous, we have g of g of f. Okay. Because what you have is that if yn because of the continuity of g. So this is what you get. And what does this mean? That is G composition F of Xn converges to G composition okay. So this is what you get. So G composition F is a map from X to Z such that G composition F is defined as G of F, G of Fx. G composition F of X is this. It is D of because of the continuity of G enables this. That is so a remark. This is for the students anyway. This composition G you could give an example for this. Okay. So that's about the composition of functions. So we have seen that sum of functions, product of functions, scalar multiple of continuous functions, they are all continuous. So also properly defined composition of functions is also continuous. Now let us work on this. Once again we take some examples. This is quite important because we work on what are called vector spaces. Okay, so suppose let norm of x normed unit space. The norm what is a norm? Norm is essentially a function defined from R. In fact, more generally, more precisely, with the following properties, that norm of x norm of x plus y or norm of ax in fact you can rewrite this for k belonging to C also, isn't it? Yeah, right now bother only about a real vector space, but it is equally well true for complex vector space also. This, of course, in R2, the usual metric simply means this, that this is what you call this length. Suppose this is x. The length is what you call norms. And the length has the property that if you scale it up, this is y, and this is ky, the norm of ky equal to odd k norm of y. And this one essentially tells that norm of x plus y. You know that the parallelogram law holds in the vector space. If you have x, y, then sum of these two vectors is given by the parallelogram law. So this is x plus y. So all it says is that the length of the diagonal of this parallelogram is less than or equal to the length of x plus length of x plus length of, that is the what you call a norm. So norm is a function from x to R is continuous. That's quite easy to prove, because you have, see, what you want to prove is this. Suppose xn, which means norm of goes to 0. This is the meaning of that. Then we have norm of is less than or equal to norm of x minus x. Therefore, this goes to 0, implies this goes to 0. That means norm x is a function, norm is a function which is continuous. Now what about the vector space operations? we are going to prove that the vector space operations are also vectors. What does it mean? It means the following. So you see that addition is an operation from x cross x to x. That means the ordered pair x, y is mapped to x plus 1. Okay. Now you introduce a norm on this. Okay. Norm on x cross x you write as, see, norm of this is on x cross x, define as okay. Now what you have to prove is this. So one thing that you can prove is that xn yn minus xn yn converges to xy. Okay. See? So we define a distance function. You define. So this is for x1, y1, x2, y2 is defined as norm of y2. So this is the definition. So you see that now you see that you define the function f what do we have to prove? We have to prove this xn yn, this belongs to x cross x. Okay, so you consider the sequence and assume it converges to xy, that is xn minus x goes to 0 as n tends to infinity. What we have to prove is this, that is f of the sequence f of x1 by n, which is equal to the sequence this is in x, of course, goes to plus 1. Okay. So you write this. So xn plus yn minus this is the distance on x. This is equal to, or this is less than or equal to which goes to 0. That means xn plus yn goes to x plus. So xn converges to x, yn converges to y, implies xn plus yn converges to x plus y. Or look at the addition function that you define from x cross x into x. Then the function is a continuous function. So addition is a continuous function. So what we can infer is this. It's a continuous function. Similarly, scalar multiplication is a continuous function defined from x by, what is this? This is equal to so this scalar multiplication is also a continuous. That's also, so you have to show this actually. This alpha n x n converging alpha x implies that's quite easy to do. We have to bring in some term. But why did I say about these two? That is the addition and the scalar multiplication. And then why did I talk about the this? Because you see that when you go for further generalization of say topological vector spaces, okay, that means a vector space with a topology imposed on it. So the topology that you impose on that is something with respect to which the addition operation as well as the scalar multiplication operation are continuous. The addition operation is defined from x cross x to x. Scalar multiplication operation is defined from r cross x to x. If you are talking about complex vector spaces, then it is from c cross x to x. Okay, so this is in a normally linear space, this is quite easy to work with. But when you start taking the situation that you have a vector space with a topology on that, with such that the addition and scalar multiplication are continuous. Is called topological I want to make some further remarks on this. So you are talking about addition as a map from x cross x to x. So when you want to talk about the continuity of this operation, you need a topology on this. What is the topology that you impose on this? And what is the topology that you have? You are already given on x a topology, and from that you can get the product topology on x cross x. So you have a topological space here, another topological space here, and addition is a map from one topological space into another topological space, and this function should be continuous. So the topology should be such that this addition operation is continuous, or what you call the vector space operations are continuous. In the scalar multiplication, it is from C or R cross again you have the usual topology on R, and R cross X you can define the product topology, and now this is a topological space. Scalar multiplication can be considered as a map from R cross X to X, and you want this also to be continuous. Therefore, whenever you try to build a topological vector space to serve some purpose in some applications, then what you do is you have to insist on the following. The topology that you impose on X has to be such that the map, the addition, the vector space addition is a continuous operation from x cross x to x, and so also the scalar multiplication is a continuous operation from R cross x to x. Okay. Then you say x tau is a vector space. Now this is because, see that if you look at this, see this addition and scalar multiplication, there are algebraic structures that you have on the set X. Okay, and then the moment you impose a topology on this, X becomes a topological space, and immediately the product topology is available on x cross x. So also the usual topology is available on R, therefore on R cross x you have a topology. So both x cross x and R cross x, C cross x in the case of complex vector spaces, are now topological spaces. So it is quite meaningful to talk about maps from x cross x to x and R cross x to x being continuous. Okay, because you, without the help of topology on both the domain and the range, you cannot talk about continuous functions. Okay, right, and this may not be a normally linear space. See, that topology may not be coming from a norm, right? So it's quite possible to generalize the concept of normally linear spaces to topological vector spaces, and in fact you require it in some context. And therefore, for analysis, you need this kind of situations, especially when you talk about all distributions and so on. Distribution theory is introduced. You need not, it is not sufficient to work on what are called normal linear spaces, but you will have to work on general topological spaces. I'll just leave that remark and just if you find it indigestible, just forget it. Otherwise, you keep it somewhere inscribed in the corner of your mind, so that at a later stage, when you come across them, you can just revisit it and try to understand it more deeply. Now, one more thing is that, okay, if X is an inner product space, R or C, you have the map the inner product of X with Y is continuous. Right, this is what you have to do. X and yn converges to xy implies xy. Okay, now this is quite easy. So inner product is also a continuous map from X cross X into C. So in particular, on if you take the case X is equal to R, the usual metric, or look at this as a non-linear space. Another example is this. If F and G continuous, XD is a metric space, then phi defined from X2 R2 defined by phi of X equal to the ordered pair fx dx, this belongs to R2, this belongs to x belongs to is a continuous function. So that's how they're all straightforward to work on. So there are so many other examples that you can put forward. And one of the things that is probably worth knowing is that suppose you define the map this is all n by n matrices. Thus defined by A transpose. This is A transpose. This is continuous. And in fact, you can consider this as an n by n vector space. See, something like this can be identified with R n square. Okay, because you write it as A, you can write it as A can be identified Now you find out what is the corresponding element of A transpose, and you can easily write down this map. So find it's quite easy to prove that it's continuous, the usual metric. Now this is also an exercise. A the map A to the power k I think there are other examples discussed in the book of commemoration or any other books which you can find out. I think there are plenty of situations that we have already looked into. Now what we want to do is make an analysis of the equivalent definitions of continuity. Okay. So I think what I do now is just recall, or I will do it in the afternoon. Okay. So with this, we conclude this definition through sequential convergence and exploration on the various examples, the concept of continuity. Now we go for a general definition of continuity. That is our task, which works not only on matrix spaces but also on general topological spaces. So we will systematically go from our model, that is R, on which you define continuity. There you can comfortably define it through sequences. Generalize that to matrix spaces. There also you can work with sequences. But then we already have another way of defining continuity on the real line. Functions defined on the real line. We know we have another definition of continuity. So are these sequential definitions and the other definition identical? That means one implies the other and the other implies this. So that we have to prove. And what are the analogs of that for general matrix spaces? And how one has to go for search for a definition of continuity in the case of general topological spaces. This will be the theme of our talk in the next 1 or 2 lectures. Thank you very much.